Welcome back once more, my fellow programmers, to this animated PLC course. This class, we're going to analyze the main differences between direction and mapping. But before that, we're going to analyze the following topics: PLC components, directives for PLCs, identifying inputs for PLC, identifying different outputs for PLC, mapping, and most of all, practical differences between directing and mapping in PLCs. Okay, now let's get to that. All right, so we start off with our PLC components. Here I have divided on my screen the embedded PLC and the modular PLC. Now, careful with this, guys. This is not a general classification between the PLC. It is a classification between inputs and outputs. Now, how does the PLC have these classifications? They have to be integrated with the PLC, or they're independent. They're inputs and outputs. What do I mean by this? PLC is a component, but it doesn't have, together with the same device, it doesn't have an input or an output, or points to connect, or sensors to connect relays, or contactors, anything. For example, here we have our PLC logo, and this is an embedded PLC. This PLC is the one same one as we have on our video, where we have our little PLC mascot, and that PLC is logo from Siemens. Now we're going to analyze another embedded PLC. This is a PicoLogix. This is embedded. And now we're going to get to our modular PLCs. I'm indicating that everything is going to be separated. Now this that we see here is a processor PLC, a CPU. Let's see if we can appreciate this. This is a very old PLC. However, it shows us the point. It's only the PLC. If I wish to connect on this side a sensor, it's not going to allow me to do so. And why? Because I would need to buy or purchase an input card. And this is only defined to connect input devices. If I wish to connect outputs, I would need to buy an independent output card. Now, what's the real classification for our PLC? Basically, we know it's low tier, mid tier, and top tier PLCs. That's the right classification. Many people get confused because they say, well, it's embedded and modular PLCs. No. Okay? General classification for PLCs is what I just said. However, we're going to review this further down. Right now, we're going to analyze their PLC parts. Now, we have our buddy PLC boy, and it's going to tell us that on the top part, we can connect sensors, okay? I can connect here one sensor, and then another one, and then a pulsar, and then another one, and another one. Talking about sensors. And here I can start connecting my devices. These are my inputs. And now we're going to analyze my feed. We know that a PLC is an electronic device, and every electronic device needs to be fed by electricity. Cases like cell phones, computers, televisions, we know that they're electronic devices. And if they don't have voltage, even though they have integrated battery, their voltage goes out and the PLC is ruined. So we need to be very careful that there always needs to be some feed to our PLC. It's very robust, but it needs to be fed through voltage, either DC or AC. The most common one, the most common voltage used in the industry is 24 volts. The industry, obviously, and also the PLCs. In our control devices, the ones that we are going to control, that signal that we assign to this device is going to be 24 volts for DC. Now, what would happen if we change it to AC? We could do that, but every PLC is different. We need to analyze its characteristics. And we also need to analyze what voltage is the one that is needed to be fed. Be very careful with this. We need to learn and know how to identify the voltage and the range. Now, the feed generally, am I going too fast? I'm going to add a note here. We have our L1 in this order. This is positively fed. And we know that, well, this is positive. Yeah, this is positive. And negatively, we would take it to our source. And here it says N. Now let's see if this is true. We have here our PLC logo. Let's see if we're able to see this. Well, you see this is backwards. Well, we have L1 and N. This is where we need to add our feed. And for example, it says here, well, it doesn't really show, but here we have our data, our feed data. We can't really see this, but it says 24 VDC, which is 24 volts DC. So this is where we need to be very careful with. And remember that our outputs, it is recommended that we send DC signals, unless we have relays for AC that can support our PLC for that type of configuration, especially if they're relay outputs. Okay? Now we're going to explain this further down the line. So then we already analyzed our feed for our inputs. Now, what happens now with our modular PLC? We also have our feed source, but it's also not integrated. We need to acquire or purchase the source, and then we should also purchase our PLC. Modular PLCs generally are used for applications that are very robust, which are, let's say, mid-tier and top tier. When I say top tier, I'm talking about some that we can integrate more networks, more devices. They have more memory and more capacity. So we can run more advanced drills, for example, for top tiers. We can integrate more axes and more servo motors. And they can take larger number of servos, which we have embedded cards in a processor. Not in the cards, but in the ports, so that we can connect through Ethernet. these are, let's say, a little bit more advanced. So that's why, since they're very advanced, especially for plants and processes that may be scalable. So let's say, for example, a customer says, this year we're going to start up this process, but whatever process. But next year we're going to get a new process over the process that we are already starting up. So then there's going to be scalability. So therefore, our customer is prepping to add more inputs and outputs for the cards that it needs. So that same PLC can control process one for that year that it's being installed and process number two for next year. So that's why you purchase the cards independently or separately. They're used for smaller applications. Yes, robust, but not so robust for mid and top tier. Now, what else do we have here? Same thing. You see, this is a module. It's a card, which is very similar. And this is our PLC, but it's very similar to our PLC. I don't currently have it physically, but I do have it in diagrams, which we're going to analyze further along this training. But it's a module. We open the lid and it has its connections, whether it has 16 points or 8 points or 32 points. Now, when I say points, what do I mean by this? It is these, let's say, for example, the places where we can connect each sensor. Okay? Two sensors can't be connected on one point. They need to connect independently. Now, let's say that these are the Borns. Now, this is one point, that's another one, and this is another one. If you notice here, we can start visualizing squares. These squares are LEDs, or LEDs. These are new processors, and the newer PLCs already have their cards in general. Most of them, actually. So we have our input card, they have their LEDs, and that LED, if that is lit up, let's say in point number one, it's because I have connected here my sensor. And here it's starting to notice something. And that helps us visually to know if the sensor is working or not. If here our sensor is lit up or it's detecting anything, it's going to power up this light bulb. If it's detecting a different sensor at a different point, this one is going to power up. Okay? Same thing happens with the outputs. So, input, digital inputs have their own module, their own card. They're called cards or modules. Okay? So now, we already see the difference, so we're going to continue observing this. Our display for embedded PLCs, we have here our face for PLC boy. However, this is our PLC. This is its display. Now, what is this for? To view what we're programming. The mid PLCs can be programmed without the need of a software or a computer. We can start programming and adding the instructions through our display. Now, why was this done? Because we really need smaller projects with embedded PLCs, or since they're for simpler PLC projects, there's not really much of a need to overcomplicate things. And that's why we have the instruction of being able to program our computer. And if we have an emergency, or if you need to create a real simple algorithm, we need to create a real embedded PLC in our display. That's what this is for. Now, what happens with our modular PLC? There is a display generally, and our new processors so that it indicates alarms and some flaws or failures. But we cannot program with our screen or modular display. Now, the difference between embedded is that we can control it and we can configure this. And we can analyze any failures as well as the embedded ones. But we can also diagnose troubleshooting or diagnose any problems or issues that we have on the network if we wish to change our language. And with our modular PLCs, we do need, by force, our equipment, our software. And our software is generally very expensive or very special, specifically for that brand. Allen Bradley has its own software. Siemens has its own. They all have their own software. And when they're more robust and bigger applications, they have that software and those licenses that you need to purchase. And with that same software, you need to program in ladder. All of these are programmed in ladder language. Okay, everyone has their own programming language, but there's something in common with all of them, which is the ladder language, programming language. Now, having seen this, what else do we have here? Our micro SD card for our embedded PLC, as we can see here. It's this little slot, but we're also changing within our different brand devices. Now, like this Allen Bradley PLC is PicoLogix. As I had said, here on the bottom part, it has a jumper system because this is a very old system. But the latest generations used to have also their USB memory slot. Now they have a jumper. But they're very much alike. Okay? As you can see here. If you see, there's some things that are going to change, but basically they're very similar. So for practical reasons, they can't change a brand unless they have very good functions, which are for the competition. So what good is our memory or the slot for my micro SD? Well, in case of an emergency, we can actually have a backup for my current PLC program, and I can store it in case of an emergency. In case something happened to our PLC and we modified something or it's doing something strange, we can input it. We can enter it. Now we have our micro SD card. We have our keyboard, which is our navigation keyboard. Now this is also very intuitive. I'm not going to really stop and explain all this because this is only to guide us and navigating in our menu to the top side, the bottom side, left or right to select different things, or selecting even instructions, or even selecting what we had already chosen, or whatever we've chosen, which let's say is our enter key. Now our back key for selection is the same thing. Okay, so perfect. In our modular PLC, some PLCs have these keyboards, these keys for our PLC, and some of them don't even have them, depending on the brand. But again, here, let's say that they're more useful because we have our option for our embedded PLC to program directly on our PLC. Now, here, it's not that important for them because what it does have is our micro SD for our PLC, but they also have an option for that micro SD slot. Outputs. We had said that our output devices are integrated in our embedded PLC. Now on this part, we have it here on the bottom part. In our upper level, we have our outputs, and we're going to place them here. For example, these are relay type, okay? And they're different from these on the top part. Generally, the more to the top it goes, they're more input than outputs. Now, this PLC can support digital inputs and outputs, okay? So zeros and ones activations. Okay, can it start up or can it not start up? There are embedded PLCs which have inputs and outputs that are analog. It's not many of them, but they still do have them. Now, this other PLC is the same thing. On the top part, this is our Pico Logics. And on the bottom part, it has its relay outputs. Okay. Now, what else can we observe? What else can we see here? The new PLC generations, for example, logo, has an Ethernet port and a communication port. What for? So that in theory, this PLC can talk to this other PLC, and we need to connect them through an Ethernet cable. Now, it needs to be both compatible PLCs with the same communication. Way down the line, I'm going to explain this in detail, step by step. So we're going to finish analyzing the components. And so digital outputs, we have a module and a specific card for these outputs, the digital kind. Now, there are other inputs, another different module, but if you notice, we're starting to group them with inputs with their corresponding signal, which in this case is analog. Okay? So these are for connecting different devices which receive analog data or outputs. If we want to assign speed, which is for certain velocities or certain speed, we need to go gradually modifying so that we can modify the hertz and at the same time modify the velocity. So we have different modules, like for example high-speed counters, which Allen Bradley has, and Siemens also, which also have a high-speed module. And we can also connect encoders. And this is to receive data. And we also have a different kind of module, which is Ethernet module, and a communication module, which is what I was saying. We can't really see this, but this is the Ethernet module. Now, what for, do you ask? So that I can connect my PLC, whether with my card or my processor, because there's an Ethernet assigned port so that I can connect this here. Now, it's going to depend, and we need to analyze the PLC brand. Okay, guys? Now, these are our main components and general components that our system, our PLC system has. Okay, guys? Now, what would happen if I wish to identify in my PLC, I wish to identify that I have here a button, which means that I can connect that button in that specific point. How am I going to indicate this? We had previously said that I really can't talk to my PLC directly and assign order or give it some orders, like by saying, well, you know what? I have a green button. Do you see it? It's right next to the bank, right where the operator is. When I press this, it should start that motor, that conveyor belt. You get it? Logically, my PLC is not going to understand. We need to speak its same language. And for this, developers and the creators for these PLCs for whatever brand have certain nomenclatures which logically have been standardized. And through the years or through time, they know how to make things easier. But we also need to assign these instructions through predefined memories to be able to identify, well, this memory is going to be an input and this one is going to be an output. This one is going to be a digital input and this one is going to be an analog input. Now, what are these nomenclatures? Okay, here, let's erase this. All right, so generally, we are assigned or we're assigned a number of numbers and letters, which are directives for PLCs, inputs and outputs, which is what I was saying in our previous video. So it says we need to identify so that I can indicate my PLC what I'm connecting here. And I need to indicate it what I'm going to use in our PLC, which in this case we're going to identify as file type. Now, what do you think this is? This means input. So this is an I. So when it says file type, this one, for example, okay, this one is on the bottom part is a different letter. It's an O. So the file type is O, which means that this is an output. Okay, so we're able to identify this. And then it says file number. And this, for some PLCs, already have them a little bit better identified. And we're going to set certain examples. Now, we can also use the number of files because there's many numbers for inputs. So the programmers and developers have started identifying them in different memories. Now, I don't want to overcomplicate this by forcing you to program, but this is in general. For example, an Animator PLC, what we did was not overcomplicating with file name, and we just removed it. But we can also add our wording directly. But I need to leave this in general. For example, these types of nomenclatures are known in our PLCs as SDC 500s, which are the older generations. And these are for our oldest PLCs. For example, for Allen Bradley, the PLC 5, to be able to identify our memories way better. But our new processors have removed certain characteristics to simplify our programming. But in general, these are mainly based in this nomenclature, our new PLCs. So again, with us, we already removed our file name or our file type. What else? Our word. Many of us know it as the module number. Now, where am I going with this? We need to know and learn how to identify where our digital input module is. Generally, when it comes to programming, we start from scratch. So this on the back, all of this, is mounted on something, okay? On an eggshell, let's say. And that's where we start adding all of our cards. Now, this is not for all brands because, and this is used because Siemens is using the 1200. And even though they do have their embedded PLCs, we don't really need our eggshell to start adding the cards independently. For example, Compact Logics, which is Helen Bradley, it's a mid-tier, does not need a rack. So that's why I just didn't want to add this directly so as to not confuse you guys. But we find the rack and we can start adding our cards. And there's a certain order. So that order, for example, for our processor, on our slot, we call it slot 0. Then slot 1, oh, this is a horrible number. Again. All right, this is 1. Sorry. Let me restart. That's 0. That's 1. That's 2. That's a 3, 4, 5, and 6. Okay? So we need to be able to identify, for example, digital inputs, which slots do they have? Or what slot number is it? This module, for example, for digital input is slot number 2. So therefore, here, our wording should really be the number in which our card is located in, what the order is. And also, aside from our embedded PLCs, you might think, well, we don't have any modules here in our inputs. Well, programmers now, or IT developers, they start their memories and they simulate as if it was a module, which is an embedded module. But it's being added right from number 0, which are starting from number 1. So we need to learn to identify from where we're able to use that module, that internal module for our PLC. But it's not really that complicated. It's either 0 or 1 if these are inputs. If they're bigger, we need to learn how to identify what group they're in. But it's basically this. This is of huge help for mid-tier PLCs or high-tier PLCs. Okay? And finally, now, through this or with this, we are going to indicate our PLC what type of device we're going to connect and for which card we're going to connect it on. Okay? So the file name or file number depends on our PLC. And the input part or the point part, as I was saying, we're going to draw it here. Let's suppose that this is our point, and I'm going to connect here a contact, okay? If we energize our contact, I'm going to assign here a PLC voltage. If the PLC detects that voltage, I'm going to run whatever action or activity. So then, our last digit is going to help us ID our point number, which in this case, with our modular PLC, if I connect something to my point 0 or my 0 point, and let's say if I connect my push button, okay, my normally open contact, if I connect it on my first input for input 0, then basically that means that I have something connected there. Now I need to learn how to identify it in my PLC. This is so this makes sense, okay guys? Our inputs, it's very, very similar. Here we have an O, and we also have a file number, which is optional, the word, the module number, and this is 0, 1, 2, 3, module number 3. So then we would have an O, 0, semicolon, 3, dash, and here we have our beat number, which is our point number, where I'm connecting my piston. And where am I connecting this? To my electro valve. Okay, for my 0, point number 3, or wherever I'm connecting it to. Now, according to our Animator PLC, the nomenclature that we added, as we can see below here, as you can see, I've already summarized it on many times. And we're also based on the Siemens nomenclature, which they also have a file number. It's not that much visible, and if it is, it's internal, as the rest of our processors. So my nomenclature is E, and this means that I'm assigning an input, which in this case is a push button, which is an image for our simulator, semicolon, 0, which is module 0, point, and these, or this is where I'm connecting something in my memory. Now, I don't want to confuse you guys, but this says this is a word. And the word is a set of different booleans. Why booleans? Because they only accept 2 states or 2 statuses. Okay? I'm also going to explain this further down. But let's suppose that I wish to identify my input and my button that I have here. And I'm saying this is where I'm going to get my signal. So I'm sending my PLC where I'm connecting to that button. So if I connect it, and these are inputs, so input, semicolon, 0, okay? This is our module, for example, I, semicolon, up to here. We're able to identify it here, I, semicolon, 0. Then we know that we have this row. So now we need to learn where to identify it. Now, where else does it say? Point 0. So the memory that we should be supervising should be this one, okay? We'll talk about it in the future. But for now, this is so that you guys can get an idea on how to identify, or why inputs, why outputs, why point 0, okay? So PLC directives for different brands, what I said. For example, Allen Bradley for our RS Logix 500, for older processors like the 500 or even the MicroLogix. Its directive is this one. And, sorry, I, semicolon, 0, this is a module, dash 0. So that means they connected point 0 to the board. Now, Siemens, as I had previously said, we ran a combination, but these are inputs, which are the module and the point. So input, module number, and board number. Now, this changes according to the brand. This point and this spot. In between adding an O, they added a Q. But it's very similar, you say. All we need to do is identify Q is outputs. Okay? So anytime that I want an output, instead of typing O, I need to type Q, letter Q. Outputs in Allen Bradley are O. With our software, again, input, module number, and point number. So then, Knowing the reason for my nomenclature is going to be very easy to assign the directives or directions for our devices for any PLC brand. So all we need to know is have this logic very well known and be aware of this. So this is a direction. As you can see, they're very similar. We just change between brands. So PLC input ID. The inputs, as I had previously said, what we're seeing here, is an input module. And and I'm going to work backwards on this, if we open our lid, if we open our coverage for our digital input, then we're going to see something very similar to this. We have its input, and we have it already ID'd with numbers. So then we need to convert with our push button. This is an electric diagram, but we need to connect a bourne for whatever input that we need to our other end of our push button, which is normally open. And on the other side, we're going to connect directly to our voltage, our positive voltage. And this that we're doing here is a bypass, because we need to convert from 12 to 24 volts. So they may be different voltages depending on our PLC, but it should be 24 volts because this is what I had said, which is our most used voltage. But it all depends on what you want to connect. Here, our voltage, our feed source, right off the bat can be 120 V for volts. Just writing this here. So this is VZA, which is AC basically. And this is converted to DC, which in this case can be 24 volts. Can also be 5 volts or 12 volts, depending on what we need. Okay? So, when we press our button, here is being interrupted because its regular status is open. So then it's not really passing through any type of voltage. And here it's basically with our circuit. So we need to allow all of our voltage to transmit on this side. It's a signed slot. And then we have our negative slot, which we need to connect wherever our PLC indicates us. This is more in general because PLCs don't really change much in our connection part. But we need to read the manual. Never get overconfident unless we've already been through that experience. And even though they say, there's a saying here in Mexico that says, even the best hunter misses the hare. But in general, this is as it should work or how it should connect, which is basically a diagram for a PLC. So we need to analyze in detail our physical PLC. We're going to see this in the future, but basically this is almost the end of the course, and I'm going to analyze these topics at a more technical part. So here, for example, let's run a drill. If we use our directive for our Animator PLC, we're going to base it off of this. So then it says here, you have a push button connected for 0 input. So I have here connected my input for my push button and 2 points, or sorry, semicolon in my 0 module And I'm guiding myself off of this one. So 0, semicolon, 0.0. So this is how I'm able to identify this push button. Okay? Now, this, where would this be connected? Supposedly a sensor. This is a level sensor. So when it detects a level, the water level, as I'm sure you probably have already seen this, where does this connect to? Which point? It says an input. This is an input. This, for example, is an Allen Bradley module, which we're using as reference. So we ran our drawing here, and it should be connected here to our sensor. Okay? Do you all agree? And points 0, module number, as we can see, it's in first position. Point 4. Here, we should connect our sensor so that our programming makes sense. So we're indicating our PLC that there's something with the physical part. Okay, the same thing goes now with our input. So in this case, we have a drawbridge, which has 2 motors, big motors, induction motors with pulley systems. There are some drawbridges that are hydraulic, but the most common ones that have huge weight mass use pulleys. Now, we need to start that motor first off, power it on. And here, we're going to do the same thing. Now, this is a output module, digital, and here we go. It's perfect. So this is very similar. Don't get confused, guys. We have a common one, we have a positive, and here, now in our output, I need to energize my relay. This is a DC relay, which basically is going to feed our motor starter, which is already energizing my motor starter. Now, how can we identify this? We have here a connection point in, sorry, this is O, 0.0. Okay, again, it takes me a while. Sorry. So it's 0, sorry, O, semicolon, 0.0. If we wish to identify what we have here. Now, if I say, damn it, I made a mistake. It wasn't supposed to be 0.0. No, actually, this one is correct. But let's suppose that I connected it on point number 2. So then it's going to be O, semicolon, 0.2. And this is how we start linking them. Everything good so far? All right, perfect. Now, guys, we're going to start analyzing our mapping. But I'd like to explain this to you with our animated PLC. So join me, guys, and I'll see you guys in a couple of more minutes. All right, guys, we're back, but in our animator PLC, so we can identify one direction and so we can identify one mapping. So now let's analyze both of these concepts. They're very similar, and that's why we don't have much information on the difference between one and the other. So we're going to try to explain with examples so that this is clearer and we can resolve any issues to see what the difference is. People say that it's very similar, but it's not the same. So that's why we don't have many topics on this, but we're going to try to solve them, okay? It's really very simple. This that we have here on our left side are our programming instructions. our instructions to be able to assign or give orders to our PLC instead of directly speaking to our PLC. These symbols that we see on our left side are the ones that are going to help us identifying in our PLC our memories, our activities, or our actions, and the conditions that we're going to be waiting for. On our right side, we have our categories, which are divided depending on the actions that we're going to keep, which in this case, our timers, our counters, our logic instructions, math calculations, jump to routine, etc. in our favorite. Up ahead, we're going to add more instructions, PIDs, motion instructions, and we're going to start complementing them. Okay? But since we're starting with this is just the beginning, we are going to add a normally open contact. So for now, these are only directions and mapping. So I'm going to explain this instruction by instruction for intermediate and advanced instructions. So I'm going to explain through examples how this is really used so that you can see. Now, when we call out for an instruction, if you notice, there's a question mark. This is an input and this is an output. And we're going to analyze this so that you guys can see how a PLC can identify the inputs and outputs in ladder diagram. But that's why this is called ladder diagram. So this is very clear. Now, when we assign and we know and we have already identified our memory or our physical point as to where I'm going to connect this, that ID is called directive. Going from not having anything in our instruction to assigning something in that memory. This is a directive, and we're directly pointing at this instruction. We're pointing to or towards this memory. Okay, so I, semicolon. In this case, the module, since it's a virtual PLC, a simulator, we have simulated our modules, so therefore they're already assigned internally. So let's say our devices have already been connected for input and output. So we're simplifying that process. Okay, so if you're ready to program only. Now output, we have here O, 0, semicolon, 0. And as we had said, input, output, okay, our word, our module, here we have 2 assigned modules internally, and our bit, or the channel, or the point, where we're going to connect, in this case, with our lamp. Now, this supposedly should be connected to this memory. O, semicolon, 0.0. So we select this, and we add it. So this that we did, this simple step is called directive. And this is where we get more concepts like indexed directive, but this is a little bit more advanced for what we should have. We're not going to overcomplicate things. All we want is to know the difference. Now, what is mapping itself? Mapping is the assignment, and we're going to direct towards our mapping. And one thing is to use our direction programming and what we developed specifically for our Animator PLC. Now, this doesn't exist for any other software, okay? Our instructions, the ones that we're assigning here, are based off of the exercises or drills. These are only to assign order to our PLC on what to do and what to expect, okay? So our exercise instructions, which is something fairly new, to oversimplify more efficiently the programming, okay? Now here we have our instructions and what we're analyzing, and here we can very well analyze if we need any more steps. Now what matters here is the I/O listing for input and output. Now this that we're doing is already our mapping, which is an assignment for our physical devices, and as we know it, and the assignment for our memory, for our PLC. Now this needs to match. Now another example, let's analyze other examples. Here in our pool for I/O listing, we have our directive and what matches for physically for that directive. Because it's one thing to have our directive, which is this. This is our directive. And what makes it a mapping is actually linking that it makes sense for that physical part with that virtual part, the internal virtual part for our PLC. So this listing that we're creating is a mapping, actually. So we need to assign or make sense I have here my physical device, and what does it match? To which point? That link is our mapping. So we can run our mapping at a programming level, for example, with program, but this is not really advanced, but it's going to make sense in the future for more practical mapping, for example, with Allen Bradley PLCs and Siemens. But in reality, we already simplified this, and you guys are not really going to run this link, okay? This is already done by this. And the mapping is for an instruction to link it with our memory, but it's the instruction that we're going to be sending out as order, which makes sense, but with our memory. Now, here, with our mapping, we need to link our memory with our device, our physical device, so that we can know this. Sensor 1. For me, it's the sensor that is till the end of the line, which is placed with our controller that's controlling whatever process. I know this as sensor 1 or background sensor. And for me, it makes sense. So I'm going to identify this. And that is going to link to our physical direction or directive, and where I'm going to link this for that memory specific. Because we need to connect to that point and input, and that input needs to make sense now for our PLC memory device. That's the difference. Okay, now why directive and why mapping? That's the difference, and this is what creates a confusion. However, this makes the difference. Okay? So this is today's topic. I know it was a little bit intense, but it's absolutely necessary. I hope this makes things much clearer. If you have any questions, leave it in the comments. And we're not done yet. So we're going to continue developing and creating more content. And we're going to talk about our more technical topics, so this makes much more sense. but I think that with this, we can start our programming. Okay? And if you guys wish to know a little bit more complex things with more advanced connections, and you need a little bit more detail with our sync source, we can also see them down the line. But in the meantime, if we wish for that continuity, you need to move on to our next video, which is basically programming. But before we programming, we're going to see, we're going to look at low tier PLCs, mid tier, and high tier PLCs. Very quickly though. And on that same video, we're going to start analyzing our ladder language diagram. And after that, we're going to program. Okay, guys? Thank you very much for your patience. I really appreciate it. Thank you very much for your time. We've gotten some very good comments on this, and I'm glad you guys like this course. So, guys, we're going to continue viewing a little bit more content. We're going to be prepared. So thank you very much, guys, and thank you for your time.